Now let's talk about the next two quasi-static processes. The first one being the isothermal process and the second one being the adiabatic process. The equation or the mathematical law that governs the isothermal process is P into V is equal to constant, and we all know that in isothermal the value of temperature is a constant value. Okay, so this is the graph which indicates PV is equal to constant. Okay, and we can say that P1 V1 is equal to P2 V2 is equal to P into V, which is a constant value. Okay, and the adiabatic process is governed by the law PV to the power gamma is equal to constant, where gamma is called the adiabatic index. It is called the adiabatic index, and the value is equal to 1.4 for working fluid air. Okay, now let's find out the work done for isothermal process, and we all know that the work done would be the area under this graph. Okay, so this is the work done. So I can write down that W1 to 2 is equal to integral V1 to V2 into P into dV. So we would be integrating with respect to V, and from this equation I can say that the value of P is equal to P1 V1 upon V. So this is this is a substitution that we can do in place of P over here. So we would get W12 as P1 V1 being the constant values, integral V1 to V2 dV upon V. Now this integral is nothing but log, so P1 V1 into natural log V2 by V1. So this is the value of work done in an isothermal process. Now if you have to replace V2 by V1 by pressure values, so you can use this expression, and this would give you V2 by V1 is equal to P1 by P2. So you can have, and P1 V1 is equal to P2 V2, so you can have P2 V2 over here, same values, and log of P1 upon P2. So this is a value that you get. Okay, now a very important thing to understand over here, but that this graph is showing expansion because the volume is increasing. Okay, so as the volume increases, so V2 is greater than V1. Okay, so this would be a value greater than 1. So this would be a positive work, because work is done by the system to the surroundings. Okay, and this ratio of pressure, because the gas is expanding, so the initial pressure is higher as compared to the final pressure, so this would also be a positive value. Okay, so in expansion the work is positive because these two ratios are positive values. If you have the graph going in the opposite direction, that is the compression, so in compression, let me use some other color. In compression, okay, V2 is less than V1, so this ratio becomes negative. This implies that the work in going from 1 to 2 would also be negative, and the initial pressure is also less than the final pressure, so this would also give you a negative value of work. So this is a difference between the compression work and the expansion work. I hope you got that. Now let's move on to the adiabatic process. Now same law can be, or the same process can be adapted in this analysis as well. So you can get P1 V1 to the power gamma is equal to P2 V to the power gamma is equal to PV to the power gamma is equal to constant, and we can have work from 1 to 2 is equal to integral V1 to V2 into P dV. Now let's get the value of P in terms of V. So we will get P as P1 V1 to the power gamma upon V to the power gamma. Let's substitute this value in place of P over here. So I would get P1 V1 to the power gamma into integral V1 to V2 V to the power minus gamma into dV. So this integral would leave us with P1 V1 to the power gamma into V to the power 1 minus gamma upon 1 minus gamma, and you have V1 to V2. So this is what you have. Let's manipulate it algebraically, and we would have P1 V1 to power gamma upon 1 minus gamma into V2 to power 1 minus gamma minus V1 to power 1 minus gamma. Okay, and we know that this is something which is less than 1, so we can make it a bit, better looking, and we know that P1 V1 to the power gamma is equal to P2 V2 to the power gamma. So when you multiply this inside, so let's first take the negative sign out. So you'll get P1 V1 to power gamma upon gamma minus 1 into V1 to power 1 minus gamma minus V to the power 1 minus gamma. Now let's multiply this with this term and with this term. So when you multiply this, you will get P1 V1 to power gamma into V1 to the power 1 minus gamma minus, when you multiply this term with this term, you can replace this with P2 V2, and you get V2 to power 1 minus gamma upon gamma minus 1. So this is work 1 to 2. Now when you simplify it further, you get P1 into V1, gamma can be cancelled out, minus P2 V2 upon gamma minus 1. Now further simplification, we can say that for the ideal gas you have PV is equal to MRT. Okay, so P1 V1 will be equal to MR T1 and P2 V2 will be equal to MR T2. So you can replace it with MR being the constant value outside, gamma minus 1 into T1 minus T2. So this is the value of work done in the adiabatic process. So note this process down and make a note of this expression for isothermal and this expression for adiabatic. Okay, now if you look at the diagrams on top, just a very small concept before we go on to the next topic. If you look at the two diagrams, both the diagrams are curved. Okay, they are curved lines. So if nobody tells you that this is isothermal and this is adiabatic, how would you come to know that which process is isothermal and which process is adiabatic? Now the difference lies in their slopes. So if you look at this diagram and this diagram, if you compare the slopes, the slope of adiabatic process is higher as compared to the slope of the isothermal process. Okay, so if you have to look at it in analytical terms, in a mathematical analysis, so if you write down the you can say the expression or the law for you can say adiabatic. Now take log on both sides, you will get log of P plus gamma log of V is equal to log of C, and this can be written as log of P is equal to minus gamma log of V plus log of C. Now this is for a log axis. So if you draw the adiabatic diagram, so this is what you get, isn't it? So this is the adiabatic diagram in 1 to 2. If I replace the value of P and V with log values, so let me write down log P and let me write down log V. So this curved line would now be replaced with a straight line, because this is comparable to y is equal to minus mx plus c, where minus m represents a negative slope. So this is a negative slope curve and a negative slope line, which is very, very evident. Okay, now similarly, if you plot this for the isothermal process, you'll get log P is equal to minus log V plus log C. Now look at the value of slope here. The value of slope for isothermal is equal to minus 1, and the value of slope for adiabatic is equal to minus 1.4. So the value of slope for adiabatic is higher as compared to the value of slope for isothermal. So this is a clear-cut indication of the concept that I told you on these two diagrams, that is, the slope will give you the idea of which is adiabatic and which is isothermal, the slope of adiabatic being the higher as compared to isothermal. Okay, so this was a very important topic to discuss, that is the work done values or the PDV work values for isothermal and adiabatic processes. Now let's go on to the next video and generalize these four processes and talk about the polytropic process, which is governed by the law PV to the power n is equal to C. Let's talk about it in the next video.